Tien-Tien, can we start?
Yes, 1 second. Okay, everything should be up. Great, well, thank you for inviting me to give this talk. So I was tasked with giving everybody an update on sub-GeV dark matter direct detection. And given that this is a workshop on...
Sorry, your
micro
is a bit low.
Is it a bit low?
Speak louder. Or...
Actually, I hear you loud and clear.
You hear?
Yeah, me too. For me, it's okay.
Can you, now? Is it okay? I can sit closer to the computer. It's okay? Let's see. Okay. Maybe it's just for Ronaldo's speakers.
Yeah, it was my fault.
Okay.
Sorry.
Great. Yeah, so I'm going to give an update on sub-GeV dark matter direct detection. And given that this is a workshop about new trends in dark matter, in particular sub-GeV dark matter, the goal of this is to kind of give a flash overview of the work that's been done in the last few years in this arena. So to set the stage, I want to kind of focus, define what I mean by sub-GeV dark matter. So here's a plot that many of us have seen before, which is the masses that a potential dark matter candidate, a particle dark matter candidate can have, which spans a huge range from 10 to the minus 22 eV at the low end to hundreds of TeV on the high end. And so classically, a lot of energy in our community has been spent in this upper end, in the GeV TeV range, which is where WIMP candidates live. And so a lot of experimental and theoretical work over the past several decades has been focused here. Another arena is in this ultralight region. So my definition of light is below an EV. Of course, people who work on axions would consider this not ultralight. But in this category, it's also very well motivated. So we have candidates such as axions and ALPS. And so I'm not going to talk about either of these when I mean sub-GeV. Of course, it's not about either of these categories. Instead, it's this in-between region. And so in particular, I'm focusing on this EV to GeV mass range. And one way to look for dark matter in this mass range is to use direct detection. So flash overview of direct detection. The basic idea of direct detection, I probably don't have to explain too much to you all, is that you have a detector with some target material, which I've indicated here in blue. And this target material sits somewhere underground in a nice and quiet spot. And you wait for a dark matter that's surrounding us in our halo to come in and interact with the target. And traditionally for WIMP searches, you look for the dark matter that will scatter off of the nucleus. This nucleus will recoil, and this recoil energy gets transferred into some observable signature depending on the target material. And these signatures are, for example, phonons, photons, or electrons. So this has been kind of the basic idea for looking for dark matter, and it's led to a very well developed clear program over the past several decades, and has kind of culminated with this plot. So this is a curve that I've grabbed from the Xenon 1-ton collaboration, which is currently with the strongest constraint. So what I'm showing here is the dark matter mass in the x-axis in GeV. So this is 1 GeV here down at the low end to 10 TeV up here on the high end. And the y-axis is the dark matter nucleon cross-section. So the probability of a dark matter and a nucleon interacting in centimeters squared. And so this blue region is the Xenon 1-ton curve, as I mentioned, from 2018. And because they don't see any anomalous signal, they can rule out this parameter space here. So meaning that we know that the dark matter nucleon cross-section a priori cannot live in this blue region. And so basically they rule out masses for a lot of the parameter space above 10 or 8 GeV or so. And the next generation of this experiment is Xenon N-ton, and it's the projections for that limit are given here in the black dashed line. And this neutrino background is a curve I got from this classic paper from 2014. And this is when you would start to see coherent neutrino nucleus scattering, and it would mimic a dark matter signature. And you would need to employ other techniques to try to differentiate between your signal and your background. So given that this is a talk about sub-GeV, I'm interested in looking for dark matter candidates that are to the left of this plot. So kind of starting at this 1 GeV, going to the left off the range of this figure. So how do we look for sub-GeV dark matter, in particular with direct detection? So there's a few different ways we can search for sub-GeV dark matter using direct detection. So I list the few different ways here. So what I'll focus on in this talk is dark matter electron scattering, dark matter nuclear scattering, absorption, and if there's time, I'll briefly mention dark matter scattering off of collective modes. So let's start with dark matter electron scattering, and we can use this method of looking for dark matter direct detection in a variety of different materials, such as noble liquids, semiconductors, or organic molecules. Let's go back to this first plot, which was the dark matter nuclear scattering kind of parameter space with the dark matter nucleon cross-section versus dark matter mass. And as I noted, the xenon 1-ton limit and also the other curves that would show up. Of course, this is a very simplified plot. There's other experiments that are looking for this as well, but all of them have a similar behavior in that they rapidly lose sensitivity once you go below a few GeV in mass. And so this is telling us that this looking for this dark matter nuclear scattering is not sensitive to sub-GeV dark matter. And so why is that? So the reason for that is a matter of kinematics. So if I have a dark matter that scatters off of the nucleus, the amount of recoil energy given to this that this nucleus would have is given parametrically by this expression here. Whereas with a dark matter that scatters off of electrons, we are given this parametric energy scaling. So let's put in some numbers. For example, if I have a classic sub-GeV dark matter, which is 100 MeV, my favorite dark matter mass, and a silicon target, my favorite kind of target, which has a nuclear mass of 28 GeV, then the recoil energy given to the nucleus is about 0.1 EV in dark matter nuclear scattering. And this is well below the thresholds of all of these experiments. And this explains that rapid loss of sensitivity once you go below a GeV in mass or a few GeV in mass. In contrast with dark matter electron scattering, because the dark matter and the electron are much better matched in mass when the dark matter is 100 MeV, you can transfer about 50 EV of recoil energy. So it's still a low amount of recoil energy, but it's at least within the realm of detectability for experiments. So given this idea of dark matter electron scattering, this was proposed several years ago by Reuven Tomer and Jeremy Martin. You can kind of recast existing experiments, in particular the liquid xenon experiments, and later on liquid argon did this as well, into limits for dark matter electron scattering. And so this is, I'm showing here two plots. On the x-axis is the dark matter mass for both figures, and you'll note that the size of the dark matter mass is now in MeV. It's in the previous plot, it was in GeV. Now we're in MeV. So we go from 1 MeV to a few GeV and a little higher on the right-hand side. So note we've gone down more or less 3 orders of magnitude in our plot, and we've gone into that sub-GeV regime that the nuclear scattering was not sensitive to. And on the y-axis is the dark matter electron scattering cross-section, so sigma E bar. Previously, it was the dark matter nucleon cross-section. Now it's the dark matter electron cross-section in centimeters squared. And the idea is you can use these noble liquid experiments that look for single or few electron signatures, and you can recast them into limits on dark matter electron scattering. So that's what we've done here, or what I'm showing here. So there's the xenon 10 limit, which goes like this, the xenon 100 limit, the recent xenon 1-ton limit from a couple of years ago, and then dark side 50. I believe they haven't updated this yet. And on the left-hand side is for a particular model where the dark matter interacts with the electrons via a heavy mediator. And in particular, in this case, there's other curves being shown here, and it's the case where I have a dark photon mediator that's 3 times the dark matter mass. So that gives these gray curves and these gold curves. On the right-hand side is the case where the mediator, in this case, the dark photon, is much lighter than the momentum transfer. And so I can categorize these types of scatterings in two ways. So the heavy mediator is categorized by this form factor, which goes like 1. It's a momentum independent scattering. Whereas the light mediator scales like 1 over q squared. The cross section goes like actually 1 over q to the 4th, because I have to square this. And given a specific model, so in this case it's a dark photon model, you can make predictions for where some interesting target regions would be. So I'm showing here in the gold and yellow curves for specific production mechanisms where the cross section would need to be for a specific dark matter mass to get the observed relic abundance. And so this makes for interesting theoretical targets for dark matter electron scattering. And we see that, okay, xenon 110 is starting to get to this curve, but there's still quite a ways to go downwards and also to the left. So you can ask, how do we start to probe more of this parameter space for sub-GeV direct detection? And the answer to that is you can move beyond noble liquid detectors and instead look at semiconductor targets. And so this has been, there's been quite a bit of work with semiconductor targets. So here's an old list of papers. And here the idea is, so in noble liquids, for example, in xenon and argon, the binding energy of the outermost electron is 10 eV or so, 12 eV. So that's the minimum amount of energy you need to transfer to the electron to get an observable signature. With semiconductors, what you need to do is to get over what's called the band gap of the material. So here's a kind of a picture of the band structure of silicon, like I said, my favorite material. And in the orange, I'm showing the valence band. So this is where the electrons live. And in the blue are the conduction bands. So these are a priori empty. And in dark matter electron scattering, what happens is a dark matter comes in and it hits one of the electrons in the valence band. It excites that electron. And if that energy deposition is greater than the energy band gap, so this white region here, this electron can go into the conduction band. And once it's in the conduction band, you can detect it. And the band gaps for semiconductor targets, so for example, silicon and germanium, are roughly an EV in scale. So this is an order of magnitude smaller than the amount of energy needed for the noble liquids. And as a result, you can probe lighter dark matter masses. So it's a similar argument to why dark matter nuclear scattering couldn't go lower in mass. Noble liquids also have a lower mass limit, and likewise semiconductors will have a lower mass limit. So given this interest in semiconductor targets, you can overlay on the plot that I showed before the reach that you would get with 1 kilogram year of silicon, assuming various thresholds. So by thresholds, it means the minimum amount of electrons I would need to detect, or the minimum amount of energy I would need to detect. So at the time when we wrote this paper, this is now 5 years ago. Well, it's been a while. The best limit, the lowest thresholds were about 10 electrons for semiconductor, for silicon targets. So that would give you comparable reach to the xenon experiments. If you lower your threshold, so you become sensitive to smaller energy depositions, you can increase your reach by orders of magnitude. So we see here the limit for 5 electrons here and here, and for 1 electron limit, which is many orders of magnitude better than the 10 electron limit. So there was a huge incentive to go down, to decrease the threshold and to increase the sensitivity to single or a few electrons. Another thing to note is that as you decrease this threshold, you really start to carve into a lot of this parameter space, and in particular, this what I was calling these theoretically interesting targets. So how do we go down? Like I said, at the time when we wrote this paper in 2015, the lowest thresholds were at 10 electrons. And so to go down to lower thresholds requires new experimental techniques. And I'll admit now that what I'm going to show now is going to be very biased to a particular experiment because I am a part of it. And this experiment is the Sensei Experiment. So this experiment, this collaboration was formed kind of for this reason, that we showed that it was really interesting to decrease your threshold because you were sensitive to so much more parameter space, and it required this new experimental techniques to get down there. And so through a collaboration with experimentalists, so this was with with this group plus some experimentalists, we created the Sensei Experiment, which stands for the Sub-Electron Noise Skipper CCD Experimental Instrument, which is funded in part by the Heising-Simons Foundation and Fermilab. And here's a photo of baby Sensei. Sensei has gotten a lot bigger since then. So Sensei is sitting inside this copper vessel. The collaboration has also likewise gotten larger. So what is Sensei? It's a silicon experiment. It uses silicon CCDs. And the idea with a CCD is you use the silicon target as the detector. And so you find CCDs, for example, in cameras, like the Dark Energy Survey uses CCDs, SDSS used CCDs. And here you have your pixel, and you have a dark matter that comes in and it excites an electron, and it drifts up, and you can start to move. Once it's liberated, you can move it around and you look for this electron. So to look for these electrons, these single electrons, requires very low noise. And there's two sources of it. It's the readout and the dark current. And so dark current you can decrease by just making things very cold and quiet. But the main problem with CCD detectors in the past was the readout noise, or the main limiting factor was the readout noise. So I wanted to show a cool little animated GIF. This was from Javier Tiffenberg, one of our experimentalists, that shows the number of electrons you can detect in a pixel. So here's an array of pixels. Let's say this is a CCD. And depending on n, here is the number of times I read out the pixels. And so on the right-hand side, it shows you the number of electrons you can detect in a pixel. Okay, so you can see that if I read it out one time, this peak is pretty broad. So there's a noise of 3.5 electrons, and I can't differentiate one electron from another. But as I, oops, does it work? Yeah, as I increase the number of times I read out my signal, you can see that this peak gets narrower and narrower and narrower until you start to actually see the 1 electron peak show up here. So I always like this this GIF, and you really just see that one pixel that has 1 electron here, and then the rest have zero electrons. And so it was this technology of reading out the signal many times that allowed us to get down to single electron sensitivity, meaning we can count individual electrons. And in that plot I showed of the direct detection parameter space, it meant that we can now go down to that green line that said one electron. Not quite there, because we still have dark counts. So we can go down to two electrons. But this was a big breakthrough in the sub-GeV direct detection kind of technology. Like I said, Sensei is not the only experiment looking for sub-GeV dark matter. I'm just a bit biased towards it because it's my experiment. But here's the current kind of state of dark matter electron scattering. So the cyan kind of bluish region here are the latest Sensei limits. Again, I'm showing dark matter electron scattering for a heavy mediator on the left-hand side versus a light mediator on the right-hand side. And you can see here's that xenon 1 ton curve I showed earlier. The xenon 10 curve is in the long dashed lines. And there's several other experiments here, right? You have Dominic Snowlab, which is another silicon CCD experiment, Edelweiss, which is a germanium experiment, CDMS, which is a silicon experiment that doesn't use CCDs, and DarkSide 50. So when we first started off thinking about sub-GeV, or I guess when Ruben, Tomer, and Jeremy first started thinking about this dark matter electron scattering, this parameter space was empty. And now we're slowly starting to carve out into here. So this is the current state as of April 2020, April of this year. In the future, there's several proposed silicon skipper CCD experiments. So Sensei will, the plan is to go down to 100 gram years, or go up to 100 gram years of exposure, which means that we would have sensitivity where this cyan line sits for both in both plots. The Dominic M experiment is the next generation of kind of the Dominic experiment, and this is going to be at 1 kilogram year. So this is an experiment that's going to be in Modane in France, and it will be have this type of sensitivity, and of course the sensitivity goes proportionally with exposure. And there's a proposal for like a giant skipper CCD experiment called Oscura, which will be a conglomeration of all these different skipper CCD collaborations, so Sensei and Damic M. And the goal here, if it gets funded, is to build a 30 kilogram or have an exposure of 30 kilogram years. And that would allow us to really get down to ridiculously small cross sections. So that's kind of something to look forward to in the future with dark matter electron scattering.
All right, so you have 5 minutes left.
5 minutes. Oh, okay. I am pretty behind. Okay, so very quickly then, another way we can look for sub-GeV direct detection is through dark matter nuclear scattering. So the kind of the traditional searches were looking for dark matter nuclear scattering, and I said you couldn't look for sub-GeV dark matter in this way because the amount of energy transfer was too small. And it's still true, the amount of energy recoil energy of the nucleus is still small, but you can look for secondary processes such as Amygdala scattering and Bremsstrahlung. So in a nutshell, what is Amygdala scattering? The idea here is that you have a dark matter that scatters with the nucleus. The nucleus recoils and it moves in particular relative to the electron cloud. At some point, the cloud is going to rejoin with the nucleus, and that looks like a boost for the electron. So this is kind of the picture proposed by eBay et al. Here in this top paper here. And this boost is going to excite an electron, and this will ionize the electron if it's enough energy. And this whole procedure relies on something called the Amygdala Approximation, which is that the structure of the electron cloud doesn't change during the nuclear recoil induced by the dark matter. And so in this way, you can factor the process into the dark matter nucleus scattering, which we're all familiar with, and a piece that kind of tells me how likely it is to boost the electron cloud from some initial state I to F. And so with this, you can kind of recast or reanalyze these electron experiments, these experiments that look for electrons into a dark matter nuclear scattering experiment. And that's what I'm showing here. So on the right-hand side is the latest result from Sensei. On the left-hand side is a figure from a paper with Josef, who's in the audience, looking at a heavy mediator and a light mediator and various projections. So, okay, I'm running short on time, so I won't delve too much into this. And this is a really active area of research. So within the last month, so these are all papers from November, there's been more work done on this Amygdala scattering because theoretically there's still quite a lot of work to be done, to be understood about this process. So it's another arena to keep an eye out. And maybe lightning flash, I'll skip the collective modes, but I wanted to talk about absorption, which is kind of the last way to look with these, for example, with Sensei, to look for sub-GeV dark matter. And this is to look for light dark matter that has to be bosonic. And the idea here is the analog of the photoelectric effect. So I have some massive bosonic dark matter that comes in. This bosonic dark matter gets absorbed by the material, and all of the energy of that incoming dark matter gets absorbed and it goes into ejecting an electron. So the theme to all these experiments is you look for electrons. And this is a really nice process because you can relate it to photon absorption, which is well measured. It's an experimentally measured quantity for various materials. And so the cross section for this absorption is directly proportional to this photon absorption cross section. And in this way, we can look for dark matter. So in particular, the interesting one is dark photon dark matter. You can also look for axionic pseudoscalar dark matter. It turns out this is not the best way to do it, but for dark photon dark matter, you can say something interesting. So what I'm showing here now is the dark photon mass. So now the dark photon is the dark matter, it's not the mediator. And now it's an EV. Sorry, the tick marks are not great, but this is 1 EV here, 10 EV here, and 30 EV here. And the y-axis is epsilon, this kinetic mixing parameter that we saw actually in Camilo's talk. And likewise, the cyan region is the Sensei constraint. And all the other experiments that look for electrons can probe this region as well. And so this is another category of dark matter candidates that these future silicon skipper CCD experiments can probe. And so if you increase the exposure, of course, you increase your sensitivity. So just to kind of conclude, I've introduced 3 ways of looking for sub-GeV dark matter using direct detection, and kind of gave you what the current state and the near future, or the future projections for these probes are. So what were they? It was to look for dark matter electron scattering. So that the goal here is to look for this electron that gets ejected from your target. You can look for dark matter nuclear scattering, and instead of looking for the nuclear recoil, you look for similarly an ejected electron. Or you can look for dark matter absorption, and again, you look for an ejected electron. And so these are kind of 3 different categories of dark matter models that you are sensitive to with these experiments. Of course, there's probably others. I invite folks to propose other different models. And yeah, I had this last thing about collective modes. This is not something I work on, so I'm was not going to go into it in very much detail. But here the idea is, instead of scattering off of single things, you scatter off of a collective mode. For example, phonons and plasmons and magnons in molecules and crystals. And this allows you to go down even lower in mass, down to milli-eV in masses. And so there's been quite a lot of work done here that I list. Probably not a complete list of folks who have thought about that. So if you're interested in collective modes, I would contact these folks instead. Okay, so that's sorry, I'm a little over time, but I'm done now.
All right, thank you. No, I think you right on time. So you
sorry for going so fast.
No, that's okay. So we do have time for questions. Any questions?
Yeah, can I ask here or in the chat?
Sure.
I do have a question. Experimentally, what is the difference between the Amygdala scattering and the electron scattering? So maybe I should show my video. Just go big.
Yeah, so experimentally, the signature is the same. In fact, also for the absorption, it's the same. So you just count electrons. It's just your interpretation of that. What caused that electron to be excited, that changes. And so the spectrum, like as a function of number of electrons, would look quite different.
Yeah, but I guess what I mean, what do you gain from is it do you gain from the Amygdala scattering over the electron scattering because of the coherence effect? Because now you're interacting with the entire nucleus except the instead of just an electron.
So I think the question is just it can be sensitive to different models. So if you have a model that doesn't couple the dark matter to electrons, then of course dark matter electron scattering is moot. And because traditionally, like, we were always looking for dark matter nuclear scattering, there's some motivation to try to do that comparison with that. So it's not that it's better or worse than dark matter electron scattering. It's just kind of orthogonal to it. For example, but if you had like the dark photon model, so that was the figure that I showed in my my talk. I don't know if I can go back. No. Okay. So this figure here, this is looking. You can do a direct comparison then of dark matter electron scattering and dark matter nuclear scattering if you have a specific model. So for the dark photon mediator, you have both scatterings, and that's what these dashed lines are using the dark matter electron projections and recasting them as a dark matter nucleon.
Okay, thank you.
Okay, so I do have a question about this one. So for instance, for the case of the bosonic absorption, how do you know whether it was dark matter which was absorbed or some photon? What's the signature? I mean,
so you can
that to dark matter?
So with the dark matter, it's going to be a very beautiful peak at the dark matter mass. So really nice, like and I think with photons, there's a broader spectrum of energies that photons can come in. So that would be a much flatter spectrum. And so that's another difference between like the absorption spectra versus dark matter electron scattering or dark matter nuclear scattering. Just like the shape of the energy spectrum is quite different. So once these experiments start to collect a lot more data, maybe we can start to differentiate between these.
Okay, we do have time for one quick question. If no, we move on. Okay, so let's continue. Thank you so much, Tien-Tien. Haibo, are you there?
Yes.
Okay, all right, awesome. So, yeah, share your screen. I will give you a 5 minutes warning, okay? So
All right.
take your time. Nice to see you again.
Nice to see you. Let me, sorry, let me turn on my video again. Okay. Can you see my screen? Well,
yes.
All right. Thank you very much for having me. And this is my first time to visit Brazil. Hopefully next time will be in person. So today I'm going to talk about the dark matter self-interactions and the small scale structure. I realized that we have already have 2 talks on related topics. So I decided to change the title slightly to emphasize the astrophysical aspect of self-interacting dark matter. All right, so as we all know that the WIMP is the most well-studied dark matter candidate. And after years of research that we have to see the WIMP signals. So I'd like to use this sentence from a famous Chinese poem to summarize the current WIMP research status. So he exhausted all avenues in heaven and the netherworld. He could not bring her existence to light. So this poem is about a love story, but I think this sentence really describes the current situation very well. I think this is a great opportunity for us to rethink our approach to the dark matter problem, in particular in terms of the WIMP. As we know that from structure formation perspective, the WIMP is a typical CDM candidate. Here, CDM, this is is so-called the CDM paradigm, where the dark matter, we assume the dark matter has all the gravitational interactions. And as we know that the CDM paradigm works very well in explaining larger scale structure of the universe, but on small scales, there are a number of issues. So I list several of them. And for some of those issues that we have debated for many years. Right? Here, in terms of small scales, I mean dwarf galaxies, superhalos, and galaxy clusters. So in this talk, I'm going to discuss some of those problems. So first of all, let's talk about so-called diversity problem. So this figure shows rotation curves for 4 dwarf galaxies, and they are chosen such that they have about the same Vmax, the maximum observed circular velocity. But if you look at the inner region, the rotation curve behaves very differently. For this galaxy, the rotation curve increases very fast. Okay, at 2 kpc, it's already reached Vmax, while for this galaxy, apparently it saturates to Vmax around 8 to 10 kpc. While these two are in the middle, and the rotation curves increases mildly, but it's not as mild as compared to this one. And so there are colored bands. These bands are from hydrodynamical simulations of CDM. And what you can see is for this galaxy, the agreement is very good. This galaxy, the CDM simulation breaks down, okay, inconsistent with observations. And these two, the tension is much more mild. So the diverse rotation curves of spiral galaxy actually indicate dark matter distributions are diverse in spiral galaxies as well. That is because the circular velocity is really a measure of the in the mass profile. And in other words, this galaxy, its dark matter can have a Cuspy profile as predicted in CDM, while this galaxy, the dark matter in the density should have larger density cores. And these two should have small cores. And so these are just 4 galaxies. But the problem is more dramatic if you look into the larger samples. So here I show you an example. If you take one galaxy, you look into 2 points. One is the maximum circular velocity, roughly is asymptotic, its asymptotic value, and you pick up a point at 2 kpc, let's say, and this is circular velocity at 2 kpc. So each blue point represents a galaxy, and what you can see is for given Vmax, right? So the spread in V2 kpc is a factor of 4, right? So for a given Vmax, it means that the galaxies should have the same halo masses, right? But you know, the spread in the central region is a factor of 4, and this diversity is all the way down up to like very high mass galaxies, and this you know the medium, the black curve shows the medium of the CDM simulations without baryons, and the red one with baryons. So the point is that the spread predicted in CDM simulation cannot accommodate the observed spread. So this is a big challenge for CDM. In the next few slides, I'm going to show you that the diversity can be explained if dark matter has strong self-interactions. So let me explain a little bit about self-interacting dark matter. So at this point, the assumption you have to make is that aside from gravity, there's collisions, there's self-interactions, and it can be measured by cross-section per mass, which is to be 1 centimeter square per gram issue, which is close to the nuclear scale cross-section. So you can estimate it by demanding collision happens in the central region of the halo per galaxy, per age of the galaxy. And once you turn on self-interactions, you ask what happens. So this plot shows a density profile, and this is CDM prediction. It's Caspi density profile. And if you wait for 10 gig years of evolution after you turn on self-interactions, you get a shallow density profile. The reason is the following. This plot shows dark matter velocity dispersion as a function of radius. Dispersion is a measure of the temperature of dark matter particles inside a halo. And this curve shows the CDM. If you go towards the inner region, the velocity dispersion is smaller and smaller. So that's the reason why the density builds up. Now, if you have collisions, dark matter particles, collisions will transport heat from the outer region to the inner region, and those inner particles will escape from the inner region to occupy a larger orbit. So that's the reason why the density drops. Another important point here is that after 10 gig years of evolution, this velocity dispersion becomes a constant. So from the thermodynamics, we learned that if the velocity dispersion are constant, then we say the system follows isothermal distribution, right? So this is the basic idea behind the SIDM. So let's see how this simple idea can address the diversity problem. So let's look at the galaxies in these regions first. These are the galaxies prefers to have a density cores, okay? Don't like density cusps. And which means, those galaxies, their rotation curves increases very mildly. And it turns out that those are also so-called low surface brightness galaxies, and which means the baryons are not so important in the central region. And if you take the isothermal distribution, here this is the total gravitational potential over the velocity dispersion squared. And since the system is dominated by dark matter, and you replace this by the dark matter potential. And from the simulation result, I just show you that, without baryons, self-interactions will produce a density core, right? So as shown here, that the gray curve is from CDM predictions for Vmax about 70 kilometers per second, and the blue band is from SIDM prediction. And you can see that the inner rotation curves decreases because of the core formation, right? To adjust the full range of the diversity, that we also need to explain the galaxies in these regions. These are the galaxies which are consistent with CDM simulations, including baryons, and they do not need dark matter cores. they need cusps, right? So early days, people thought, core versus cusp problem. Always thought that maybe in dwarf galaxies, you always see density cores. This is not the case, actually. You see both cores and cusps, depending on the galaxies. And most of those galaxies are so-called high surface brightness galaxies, which means the baryons dominate the central region. In particular, the stellar mass dominated the central region. And you go back to check the isothermal distribution here. Now you can replace the total gravitational potential by the baryonic contribution, right? So now what you can see is now the central dark matter density is sensitive to the baryon potential, sensitive to the baryon concentration, right? So this plot shows the density profile of dark matter, and the CDM, this is the initial condition, and this orange curve is dark matter SIDM only without baryons. Now, if you increase baryon, add baryons and increase the baryon density or baryon concentration along the vertical direction, what you can see is the central dark matter density increases accordingly, right? So the point is, in SIDM, you can get both cores and cusps, right? So here, this curve, certainly you have very large density cores, but if you add baryons, increase the baryon concentrations, and its central density increases at least by 1 order magnitude in the example we showed you. So with this, we can explain the full range of diversity of rotation curves of spiral galaxies. So we actually take, in a recent paper, we take 135 galaxies, and which is the largest data set we can get in the literature. And we analyze the data and use SIDM to fit the data, and we can fit each of the rotation curves. So here we show you a few examples. We divided those examples into 4 mass bands from the small dwarf galaxies to medium-sized galaxies until like Milky Way-sized galaxies. And you can see for each being that, look at the inner region, the spread around 1 or 2 kpc is really a factor of 4, right? And you can see here, and you can see here as well. And the point is that the spread really reflects the fact that dark matter distributions are very diverse in the inner region of spiral galaxies. And you can see that the SIDM explanation is very good.
Hi, Bob.
Yeah.
Hey, sorry, can I just ask? I'm curious, what do you actually fit in those? I mean, how predictive is the model for those fits? Because you take the velocity, asymptotic velocity as an input, right?
Yeah. So we use asymptotic velocity as the input. So then there's also another parameter is mass to the light ratio, because you observe the luminosity, you observe the mass. So, but there's like a reasonable range on these 2 parameters. And there's additional constraints from halo concentration. So given Vmax, essentially, the NFW profile has 2 free parameters, but they are strongly correlated. Actually, there's essentially 1 free parameter. So essentially, you vary the Vmax to fit try to match with the data in the outer region, and you vary the concentration, but that is very strongly constrained from cosmological observations. Then the rest of it just predictions. Roughly speaking, you choose a halo such that you can fit this region, then in the inner region, you almost is a prediction. Bear the mind that you can vary the concentration a little bit. That's it. Yeah, so we fix the cross section here. All right.
Oh, sorry, I was muted. So okay, I'll ask in the end.
Yeah, okay.
Asking,
yeah, right. Thanks.
I'll ask in the end.
Yeah, okay. Yeah, so we also did a kind of systematic study with other kind of models. Let's say the CDM model with strong feedback, weak feedback, and so on and so forth. And did a statistical analysis. The conclusion is that SIDM provide the best explanation for the data. And this solution is very kind of simple in the sense that you only need to add one cross-section per mass, so one parameter, add one parameter. You can explain the full range of diversity of rotation curves of spiral galaxy, which Puzzle does for more than 25 years. So if you take a model seriously, you wanted to apply it to other systems. So let's move on to think about satellite galaxies of the Milky Way. These are the systems which are different from field spiral galaxies, because those you see the blue blobs. Each blob represents a dwarf galaxy of the Milky Way. So they are evolving inside of the tidal field of the Milky Way. Okay. So let's take two examples. One is Draco, the other is Fornax. And if you plot the density profile of these two galaxies, dwarf galaxies, inferred from stellar kinematics of the system, you can see that the central densities differ quite a lot. So Draco has very high density, and Fornax has very low density. The difference can be 1 order magnitude. So in other words, dark matter distributions are also diverse in satellite galaxies. Sorry, let me close the windows. There's a garden outside. Okay. That's a problem working from home. So dark matter distributions are also diverse in satellite galaxies, right? And naively, if you take the analysis we did for spiral galaxies, and you can, you naively you get for Fornax, you have to have larger cross section, 10 centimeters square per gram, but for Draco, essentially small cross section, which is actually Draco is completely consistent with CDM, right? So then you generate a tension within the SIDM model. And of course, at some point your heart is broken that, it works so well for a few of galaxies, why it breaks down for satellite galaxies. But satellite galaxies are subtle because they are evolving, they have been evolving in the tidal field of the Milky Way for over the past 10 gig years, right? So something gonna happen if the object is moving around the tidal field of Milky Way. So here's a little movie to show you what happens. So this blue blob indicates this is a dark matter halo. If you look at the inner region, it's very bright. It means the density is high. And it evolves in the tidal field of the Milky Way. We ask what happens. Right. So what you see is that, after this halo evolves inside the tidal field, you even could not identify where it is after the evolution. The reason is that the tidal field, the tidal interaction, has stripped away more than 90% of the halo mass from the object. Right? So you have to take this into account, which is really nonlinear process. So if you take this into account, you realize that you actually can explain the bigger difference in the central density. So here, this is a solid curve. This curve is for Draco, and this curve is for Fornax. And if you, after the tidal evolution, we use embodied simulation to model the tidal effect. And what you can see is the two dashed curves are initial condition, right? So they are quite close. If you look at the central density, they are quite close. But after the tidal evolution, the spread becomes large. You can get 1 order magnitude of difference in central density. So there's, what happens is for Fornax, actually, because self-interactions is in the core expansion phase, that the combination of self-interactions and tidal stripping, tidal interactions will bring down the central density dramatically. So even the 3 centimeters square per gram works. While for Draco, here we see that actually the tidal interaction will speed up a process called core collapse, and its central density increases instead of decreasing, right? So this example to show that SIDM can explain diverse dark matter distributions in both satellite and field galaxies. Let's move on to think about 2 other systems. These are the so-called ultra-diffuse galaxies, which were just discovered a couple of years ago, or 1 or 2 years ago. These are the 2 older galaxies which have been discovered so far, that they contain very little dark matter. Astronomers show that you don't need dark matter to explain all the kinematic data. So this is called a NGC 1052 DF2. So why there's a bigger, front name here is that because this is very close to our elliptical galaxy here. This is called NGC 1052. This is called a DF2, DF4. These two galaxies contain very little dark matter. So why this is kind of intriguing or crazy? Think about Milky Way. For Milky Way, the ratio of the dark matter mass to the stellar mass is about 30, right? For DF2, DF4, this observed stellar mass is about 10 to the 8 solar mass. And if you take the standard kind of abundance matching, or halo mass and the stellar mass relation from standard prediction, you would expect this ratio to be 200, which means dwarf galaxies are more dark matter dominated, right? It's a reasonable expectation. However, observation shows that this ratio is about 1 or less than 1. You actually don't need dark matter to explain the data. So this is really part of the kind of astrophysics. So our expectation is that, these two galaxies most likely to be satellite galaxies of the massive elliptical galaxy nearby. And the tidal interactions between the satellites and the elliptical galaxy can reduce the mass of these two ultra-diffuse galaxies. We model this by using embodied simulations. So for example, the initial halo mass, we take a 10 to the 8 solar, 6 times 10 to the 10 solar mass, and the stellar mass is 3.2 times 10 to the 8. The ratio is about 200, right? This is the initial condition. And you put in the tidal field, you let it evolve, and you can see that the halo mass is reduced by a factor of 400. And the stellar mass is about reduced by a factor of 2. So if you take the ratio, it's about 1, right? So that's great. Now, you may wonder that, the tidal interactions will also occur for cold dark matter, CDM as well, right? So indeed, this is the case. So here we consider 4 models as CDM, SIDM 3, SIDM 5, and you can see this is the bound mass as a function of time, and when it evolves, the bound mass becomes smaller and smaller, right? So that's what we needed to explain this ratio. However, there's a price to pay. For CDM, the concentration, which measures how dense the dark matter is, which have to be 4 sigma below the cosmological medium. So which means this, for CDM, it's really, really unlikely, which is 4 sigma below. While for SIDM, it's more close to the medium concentration. Let's say if you assume 3, it's about 2 sigma below medium, which is low, but 2 sigma is not too bad. Well, if you consider SIDM 5, then it's almost, you can get it with almost a medium concentration. So
I have 4 minutes to go. Okay. 4 minutes.
All right. SIDM will lead to core formation and boost tidal mass loss. So our conclusion is that DF2, DF4 are most likely to be satellite galaxies of NGC 1052, which actually have been confirmed by recent detailed observations. And they are much more like naturally to be realized in SIDM than CDMs through tidal stripping. So let's consider, we also did an analysis for galaxy clusters. Those are the biggest systems. For example, this cluster has a mass about 10 to the 15 solar mass. And we show that most of this 6 relaxed galaxy cluster we have analyzed also prefers to shallow density profile compared to CDM prediction. And some of the 1 or 2 of those galaxy clusters actually slightly prefers to have a quarter profile. And what's really interesting is that for clusters, it turns out in the outer region, it matches to the NFW profile very well. And the cross-section you need to explain the data is about 1 order magnitude smaller than the cross-section you get from dwarf galaxies. The cross-section to be about 0.1 centimeter square per gram for clusters, right? So in this talk, I will show you that observations from ultra-diffuse galaxies, Milky Way satellite galaxies, spiral galaxies, and galaxy clusters, and overall impression is that the dark matter distributions in galactic systems are very diverse. And we have shown that SIDM can explain them over a wide range of the galactic systems. You know, the mass really spans about 7 orders of magnitude. All right, so what are the implications in terms of the particle physics models? Well, there are 2 challenges. One is you have to have a large cross-section, as I said, which is close to the nuclear scale cross-section. And you also need to accommodate kind of the velocity dependence, right? So on a cluster scale, the cross-section really has to be small. Actually, you can achieve this by considering a simple model. Suppose dark matter has self-interactions with a mediated particle, which in the non-relativistic limit, you get like a Yukawa kind of model. And it has 3 parameters: coupling constant, mediated mass, and a dark matter mass. And let's say you fix the coupling constant, you know, to be fine structure constant you observe in the standard model sector. And what you can see is that there's a closed region which can explain observations that, you know, all the astrophysical observations we have discussed. It really predicted, let's say, dark matter mass is 15 GeV, mediated mass is 17 MeV. So this kind of measurement is independent on whether dark matter has self interactions with standard model particles or not. So I would call this a nightmare scenario, but it's not hopeless, right? So this is just one example to show you, right? So you can vary those parameters and the coupling constant, for example, or you can take a different model. So I believe Lee and Chu have discussed the alternative approaches to fitting those parameters. All right, so the last topic is that you may wonder that, well, whether SIDM has some unique prediction that there's no way for CDM kind of to mimic it. The answer is yes. This is a gravitothermal catastrophe or gravitothermal collapse. So the idea is the following. So you have seen this velocity dispersion of functional radius, and at the first stage, self-interactions will transport heat from outer region to the inner region, and you get isothermal density profile, right? But if you let the halo evolve further, what really happens is that, you know, actually velocity dispersion profile increases towards the inner region. So at this stage, heat will go out because the inner region is hotter than the outer region. Heat will go out. Then the inner region will collapse further, right? The reason is why this happens, because for a halo, it has negative heat capacity, right? So it's a gravitothermal system. It has negative heat capacity. And if you extract more heat from inner region, the gravitational collapse occurs further and the system becomes hotter, right? So this is a little movie to show you what happens. Initially, the CDM profile and the density profile becomes shallower, right? So this is the first stage that you see. But if you wait long enough, you can see that central density gradually increases. And at late stages, and then the density increases crazily, right? So eventually, it becomes something called a single isothermal profile, actually much more cuspy than the NFW profile you would expect, right? So now you may say, well, what are the observational consequences? Well, there's one bonus you get from this idea is that it may help you to explain the origin of supermassive black holes you observed in the early universe. You know, astronomers observed black holes mass of 1 billion solar mass when the universe was about 800 million years after the Big Bang, right? And so I just show you one curve. You see that this is the most challenging one. Right? This one had a mass about 2.2 times 10 to the 9 solar mass, a ratio of 6.7. So its accretion rate actually is very, very, observed accretion rate is very, very small. So essentially you have to have a seed mass, very massive seed mass very early on. While this curve shows how the SIDM collapse, if you have a halo about 2 times 10 to the 11 solar mass, at the early stage, it can collapse to see that this massive black hole, right? So this region is the prediction from direct collapse of the gas, which like from astrophysics, and you can see that it misses by about 3 orders of magnitude. What really interesting is that the cross-section you predicted in this kind of scenario is broadly consistent with the cross-section we need to explain the dark matter distribution in spiral galaxies. Lastly, that in September there's a nice science paper using observations of strong lengthening to put some constraints on the density of the galaxies inside the galaxy clusters. The whole story is a bit complicated, but let me just highlight their result. So this plot shows the circular velocity, maximum circular velocity, as a function of the mass of the galaxies inside the galaxy clusters. So for a given subhalo mass, the galaxy mass, and the maximum, if the maximum circular velocity larger, means it's more dense. Okay, so the black curve is from their lengthening observations, and each dot, the dots are from their simulations, and this yellow curve is from CDM medium simulations from a medium from the CDM simulations. And what you can see, there's a bigger gap, right? Certainly there's a gap. So in this theory, actually in this observation shows that CDM substructure in the clusters not dense enough to explain the observed data. And while in SIDM case, what you can see is that if the core collapse occurs, you can easily get a large central density. So let me just show you an example. Follow this curve. This is the tidal evolution of this kind of galaxies inside of the galaxy cluster. When time goes on, the subhalo mass becomes smaller because of tidal stripping, while the central density becomes smaller at the first stage. But at a late stage, the central density increases because of the core collapse. Well, for CDM, it just stay here, right? So it's easy to get, relatively easy to get central density, high central density. So we might have seen some gravel thermal collapse of the SIDM halos. I'm out of time. Let me just quickly summarize. So in this talk, I try to show you that there are strong hints and also probably evidence for dark matter self-interactions from long-term perspective that, there are, in astrophysics, there are, future upcoming observatories and telescopes will further help us to narrow down, to explore the self-interacting nature of dark matter. I didn't have time to talk about how it can predict actually the Ricci phenomenology as well. So in this case, suppose this mediator particles can interact with standard model particles, then you can get all direct, indirect detection signals and also the collider surges signals. And the overall comments is that if you consider light dark sectors and you consider some resonance effect, then SIDM is really relevant for those searches. Thank you so much.
All right, thank you so much, Haibo. So we have time for one question. The further questions can be left for the discussion section. So one question, anyone?
Can I ask?
Sure.
Yeah, actually, hi, Javier.
Hi.
Your explanation of this diversity problem, I just wonder, would you get some like anti-correlations between the shallowness of the halo with gas mass or something like that?
Yeah, exactly. So we have a paper early this year. So there's a correlation between the baryon mass or baryon concentration versus the slope. Okay. Yes. So there's a correlation. So essentially, if the baryon mass is baryon concentration or baryon density is higher, then the halo, the slope is more cuspy. So yes.
Yeah, actually, because I just want to see whether it's different from this feedback, because in that case it's related to stellar mass. Like I wonder whether this case is directly related to gas mass or this baryon mass.
Okay, good. So in those spiral galaxies we choose, the majority of them is dominated by by stars. Okay, by stars. So the gas, there are very few, very tiny ones actually. The gas is important, but there are galaxies, spiral galaxies called recently found ultra-diffuse galaxies in the field, and those are the galaxies which are dominated by the gas, actually, gas. Okay. So, but for the system we analyze here, is most of the galaxies dominated by stars. Yeah. The best,
Okay.
usually the best concentration is low compared to the stellar concentration. Yeah.
I see. Okay, great. Thank you.
Okay, all right. So thank you so much, Haibo. Let's move to the last speaker, Roberto. You please share your screen.
Okay, I think you can hear me. So yeah, first of all, I want to say thanks to the organizer of the workshop for the program that is going on the next days. These days also is very, very interesting. All the topic that this is covering, that is going to be covering, especially because the idea of the workshop, as is written in the title, is to get the new trends in dark matter. So connected to that, my talk is basically a model of TeV dark matter that is going to be the other trend, I guess, in the workshop, because now in the morning we have all the talks talking about sub-GeV dark matter or light dark matter. In my case, I'm going to go to the heavier spectrum, in the heavier trend of the dark matter scenarios. So the talk that I'm gonna, the model that I'm gonna explain is a type 2 Scotogenic model. It's just a name that we gave with my collaborator Matthias Pierre from the IFT in Madrid. So the idea is just to present to you all these new features that are in this model. So first of all, just in case of you don't know where I am, I'm in Antofagasta. That is a city in the northern part of Chile, very far from everything, let's say, because we have surrounded by the Atacama Desert. But nevertheless, there are a lot of science going on in the same part, in the sense that around Antofagasta, we have places like the ALMA telescope, the Atacama Large Millimeter Array. Maybe in the future, maybe the SWGO is going to be a gamma ray observatories. The CTA South place is going to be also close to Antofagasta, like 3 hours by car. Also the BLT, and of course the most nice stuff that you can see here beside the desert is you can see the whole Milky Way with your naked eye, and you'll be amazed with so dark the night that can be in the desert. Anyway, so the talk, basically, I did like a brief introduction to talk about the connection, the possible connection between dark matter and neutrinos, and to end with what is the model of the dark matter itself. So, and finally with the conclusion. So let's start with the very basic, like we already know that, I guess it's not doubt that the standard model is our masterpiece of theoretical construct for the particle physics that is basically is based on symmetries. All whatever that we can see in the standard model and all the particles that are fundamental and force carriers, so on and so forth, are just based in symmetries that produce such a masterpiece that is the standard model. However, the standard model only accounts for the particles that have been observed, and we still have at least 2 evidence that the standard model has to be enlarged, to extend it in some way, because we have to include other type of phenomenon like dark matter itself, what is the origin of dark matter, and the other case is the neutrino masses, because we know that in the standard model, neutrino masses are technically 0 in order to preserve all the symmetries of the standard model. So in that sense, we go first with the first proof of beyond standard model physics, that is dark matter. We already know that dark matter has very strong or very nice hypothesis that suggests that not all the matter in the universe is only visible matter. So there is a part that is not interacting as often as we know with other particles in the standard model itself. But in any case, this extra component of matter, it has a very large imprint in the galactic and the universal evolution, in the way that it's supported by the dynamics of cluster of galaxies, the CMB, baryon oscillation. Even though we don't know the exact nature of dark matter, we know that it's there, and it's at least 85% of the total matter in the observable universe is dark matter itself. So this is a very important proof of that we still don't know most of part of the observable universe. Anyway, so one of the nice stuff when dark matter is embedded in the context of particle physics is, in order to explain all the dark matter relic abundance and how this dark matter was created from the beginning, from the beginning of the Big Bang, we have the connection between the different dark matter search strategies, like indirect detection, in which we wait for dark matter to annihilate in dark matter halo and producing standard model particles that can be observed as gamma rays, cosmic rays, so on and so forth. Direct detection, like there was the talk of Tien-Tien that it was talking about the scattering of dark matter on CCDs, particle colliders, et cetera, et cetera, et cetera. So we have all this bunch of new strategies to look for dark matter. Nevertheless, they must be connected, but by the mechanism, how the dark matter is produced in the early universe and how this dark matter is, how abundant is this dark matter nowadays. So in that all these cases, we have all these connection that makes any particle model that has a dark matter candidate to fulfill all of this class of constraints. So on the other side, we have neutrinos that are very interesting particles by itself, especially because there are many Nobel Prizes surrounding different aspects of the neutrino phenomenology. But in the standard model itself, we already know that neutrinos are massless, but with at the same time, the neutrino oscillation is a proof of neutrinos are massive, and there is no mechanism within the standard model to explain why this observable has, this neutrino has such a large mass, even though they have to be zero mass itself. So in that case, this kick on a lot of work in the theoretical side to produce different mechanisms to generate, how to generate masses to neutrinos. So in that sense, the easiest way to produce massive neutrinos in the standard model is via this WIMP operator that is just a construction that is gauge invariant, so preserve all the symmetries of the standard model, the gauge symmetries of the standard model. But the problem that is generated a dimension 5 operator that is not renormalizable, so it could introduce potentially other problems in the model itself. You can construct it, you can add it to the standard model, and you don't have to worry about the neutrino masses. I mean, to add a new content, but the non-normalizability of the model is going to spoil everything. So in that sense, in order to avoid this problem, people try to construct a mechanism that generate this dimension 5 operator. So in that sense, the easiest or the most simple or the minimal scenario for the neutrino mass mechanism that are in the literature are the so-called seesaw mechanism that basically has different particularities, like the type one seesaw basically adds a right-handed neutrino to the standard model. In that sense, this right-handed neutrino is as a fermion singlet, so it doesn't have any charge with the gauge structure of the standard model, and you can generate the neutrino masses depending on the vacuum expectation value of the Higgses and so on. The type 3 scenario is very similar to type 1, just that you add a fermion triplet, SU2 triplet, that doesn't have hypercharge, and you generate exactly the same structure that the type 1 seesaw. The only one that is different of these minimal types 1 to 3 seesaw scenarios is that the type 2 case, you don't need to add extra fermions, you just need to add SU2 triplet scalar that interact with the Higgs and can generate as well neutrino masses, Majorana neutrino masses for the fermions. So you don't have to add extra fermions, just add an extra scalar. So in that sense, beyond the 3-level mechanism that are the seesaw, there are the so-called radiative seesaw, going to one loop in the sense that 3-level processes are forbidden in such a construction. And among all these radiative seesaw that you can find a very nice compilation of all the models by Diego Restrepo, there are 2 types or a class of models that are called Scotogenic, in which neutrino masses are generated via loop processes, at one loop in this case, and at the same time, the particles that are inside the loops potentially could be also a good dark matter candidate. So in principle, there are different models of Scotogenic with the Scotogenic class. Can be very broad, but in principle, there are kind of 2 classes that use like base or inspiration. There's type 1 and type 2, and type 1 and type 3. Sorry, I didn't change it the last time. Type 3 structure for the 3-level seesaw. So in that sense that you have the scotogenic model, type 1 scotogenic model, that you add a right-handed neutrino, or in this case, a right-handed, a fermion singlet, but which is stabilized by an extra symmetry that protects the loop that is a Z2 symmetry. And in that sense, you can have in this type 1 scenario, you can have potentially dark matter candidates like the Majorana fermion or the two neutral CP-even CP-odd scalars that are coming from this SU2 doublet. In the type 3, very similar. You have also the candidates coming from the scalar doublet, but the neutral part of the fermion triplet is going to be your dark matter candidate. So in that sense, you have the two. It's just taking the type 1 and type 3 seesaws and make it to close the loop, and you can have a very interesting model because it's mixing neutrino phenomenology with dark matter phenomenology. So what is our model, the one that I'm presenting now, is basically trying to construct a Scotogenic model, but using the diagram that was in the middle between the two seesaws, the type 2. But in order to do that, we have to enlarge the scalar sector and the fermion sector in such a way that to be able to have a mechanism to generate neutrino masses. So in that sense, the minimal model that we produce is basically you need a scalar triplet with hypercharge that is similar to the delta in the type 2 seesaw. You have to add a new hyperchargeless scalar triplet. And also you have to add vector-like doublet fermions in order to construct a non-zero neutrino operator. So in that sense, with all this minimal extra field that has to be included in the standard model, you have to potentially 3 dark matter candidates. One CP-even scalar, a CP-odd scalar coming from the mixing between the two scalar triplet, and one Dirac fermion that is coming from the vector-like doublet fermion that is in the model. So what is the nice stuff that in principle we still have kind of reassembled what is observed in the normal scotogenic, but in this case is just included this triplet inside. What is going to be if you want to see the chart assignment, basically the new fields, even though there are more than in the typical scotogenic type 1 or type 2, anyway is very minimal. It's just the vector-like fermions and the two triplets, and you don't have to add any other singlets or so on and so forth. Just this is the minimal structure. So besides, as I said before, we need to include this Z2 symmetry to forbid the 3-level processes and only have the 1-loop processes, but this is common to any scotogenic scenario. But when you have to deal with the construction of neutrino masses, values, minimization of the scalar potential and stability and basic dark matter phenomenology, you finish that the only feasible candidate that works in this model is only the scalar, the CP-even scalar. The CP-odd scalar always is heavier than this one, so it cannot be the dark matter candidate. And the Dirac fermion couples too strong via Z channel and is ruling out by direct detection, basically. So if you want to see what is the different structure inside in the model, you can see the Lagrangian of the model, and in principle you have these Yukawas that here that are participating to generate the neutrino masses. And this term that is essential, that is similar to the lambda 5, in case of the scotogenic model, lambda 5 is the coupling between the two Higgses and the etas, the doublet. But in this case, it's the one that is mixing all the 3 ways, the 3 scalars in such a way that you can generate this CP-odd structure for the Majorana mass matrix. Anyway, so with all of this, we started to study what is the phenomenology of the model. In principle, the first key ingredient is to have neutrino masses. This model in the minimal construction, it generates 2 neutrino masses that are non-zero and one that remains 0 because of the structure of the Yukawa fields, the Yukawa coupling, basically. You can generate what is the neutrino mass matrix without any problem. And then one of the nice stuff that even though the neutrino mass matrix could be very complex, it's easily parameterizable in terms of the observables of the neutrino sector. So in that sense, basically the Yukawas are just normalized to these Yukawa hat terms, time this term with the phi of n, where phi of n depends on the ratio between the observed neutrino difference square, the atmospheric and solar, and the size of this Yukawa, one of these Yukawa depends on the other. So in that sense, all the neutrino physics is adjusted to reproduce the best fit, the normal order best fit. This is was one of the benchmarks that we use. We keep always the neutrino masses in that fixed value. So now talking to the part that is, for me, is could be also more interesting, is the indirect searches channel. So in this case, as you saw in the scalar potential, it's very rich because there are a lot of couplings between the different triplets and the Higgs doublet. But nevertheless, the model behaves like two classes of models that are in literature. Like there are the typical channel of the Scotogenic construction, that are the one that annihilates into leptons mainly, and neutrinos, charged lepton and neutrinos. And then there are the other ones that are similar to, or exactly the same in some aspect, to the minimal dark matter scenario. So in case that you have large triplet or quintuplet or so on, or SU2, that they like to annihilate largely to gauge boson. So in that sense, this model mixes some phenomenology proper from minimal dark matter scenarios with phenomenology from scotogenic scenarios. What is the difference between one of the other? Usually scotogenic tend to be in the order of the 100 GeV dark matter range. Meanwhile, the minimal dark matter scenario, they like to be in the TeV scale. So it's completely different energy scales for the masses. So in that sense, when we go to analyze what is the indirect searches, for instance, the W channel, we can see that basically this is the typical behavior when your dark matter likes to annihilate into W boson, that is the typical from minimal dark matter scenario. As you can see here, we are in the range of from the 700 GeV up to 30 TeV, that is the value that is compatible with observables in the radical abundant observables. And you can see here from the different points that, for instance, the blue points are the ones that might be excluded by xenon 1 ton. And green points are the ones that would be in the sensitivity of Darwin direct detection experiment. The ones that are red, that are between Darwin and the neutrino floor, and the ones that are black that you can see is the ones that are below the neutrino floor. So in some sense, those are hopeless to be observed. Another stuff that is nice of the model, that we are in the range potentially discoverable with Hess. I mean, Hess is already pushing a constraint on this model, but it's going to be for the next future of the CTA sensitivity line in the W channel. This is nice because it's a model that potentially could be observed with CTA, but besides the channel going to WW, one of the particularity of this model that is not in the minimal dark matter scenario for these TeV cases is the potentiality that the flux of annihilation into tau leptons is very bright, that also is in the range of the future CTA. So in that sense, also part of the model could be explored using CTA, but in a leptonic channel that is kind of new in this sense for this class of scotogenic models in this range of masses. But beside of that, then there is the complementarity searches, because the same structure that connects us dark matter with neutrino physics is going to be also very important to produce large fluxes of neutrinos. So in principle, future KM3net going to neutrinos, I mean the sensitivity line for KM3net also is in the reach of the parameter space that produce these models, of the observables of this model. So in that sense, complementarity between CTA, KM3net, the W channel, tau channel, neutrino channel is very interesting because of the potentiality that in the next future, next 5 years, 10 years, all these experiments are going to be running. So it could be potentially interesting. So besides the indirect detection capabilities of this model, there are the direct detection, and in this case, most of the scotogenic, I don't know if you know these scotogenic scenarios, but most of the scotogenic scenarios lacks a very strong connection with direct detection, because usually, if in the case of fermionic dark matter cases, is only loop processes the only connection that has with the decoupling with the quarks. So in this case, since all dark matter candidate is a scalar, there is first of all a tree-level connection in interaction with the quarks via the Higgs portal, but also there is a large component related with the electroweak loops, with the connection via the Z and loops and so on to connecting to the quarks. What is the nice stuff? That basically all the scan in the parametric space doesn't change too much if we consider one loop or tree level. Just you can see that here there are some points that tend to disappear to reallocate in this range from the other side, just connection. But here you can see the potentiality to be observed in direct detection experiment. For instance, all this part that is below this line should be already observed with xenon 1 ton, but all this part, the green points, are the ones that are very interesting, because when Darwin is going to start to take data, it's going to be a model that could be explored in this scenario. Also, well, there are these parts with the neutrino floor that is going to be for future dark matter direct detection searches. So just to finish, because it was just to present the model and the capability of the model. First of all, to say that this Scotogenic scenario are very appealing because of trying to connect two parts, two proof of physics beyond standard model that there are happening nowadays is neutrino mechanism for the neutrino masses and dark matter itself. So it's kind of a nice interplay or interconnection between two different sectors that should be discovered or should be researched about. And of course, the Scotogenic scenario itself is also interesting because it produces a way to explain why dark matter is stable and why the smallness of neutrino masses due to the connection via the one loop processes. And in this case, this type 2 seesaw Scotogenic model that I'm presenting here, is very interesting because it's a rare model in which you have a dark matter, a TeV dark matter candidate. Usually, most of the model of the WIMP models tend to be at most 1 or 2 TeV if they have a strong connection, like in the minimal dark matter scenario, but tends to be very mono channel in the sense they like just to annihilate into W bosons. And to end with my talk is basically to say that in the future this model can be potentially explored because of this complementarity between different experiments that are in the near future are going to be running, like CTA, ChemTreeNet, Darwin, or in the case that the SWGO Gamma Ray Observatory here close to Antofagasta also is going to be in the reach of the TeV gamma rays. So that is basically the idea of the why. In some sense, this is not for sure. This model is not a trend, but in the sense that to make research in the sector of models producing TeV dark matter candidates, it's also could be a very interesting trend for the future for the area. And that's all. Thank you very much.
Thank you, Roberto. So we do have time for questions. Anyone?
I have a question, Roberto. I'm Laura. Hi. So I have a question about, maybe I missed the point, but why do you focus on multi-TeV dark matter? You have absolutely no candidate to lower masses.
Why? Sorry, why we focus on multi-TeV dark matter?
Yeah.
Basically, I mean, in the beginning when we were working on the model, we didn't think that we are going to have a TeV dark matter. We just focused on to construct this type 2 Scotogenic model and to analyze the case. But all the relic abundant constraints pushes us to be in the TeV region, especially because the large annihilation into Ws. So you cannot have lower than 700 TeV, otherwise you have too much, too few dark matter. And if your dark matter is only annihilating to W boson, if you go beyond 1.15 TeV, you remain with too much dark matter, and therefore all the other annihilation channel coming from the Scotogenic model allow us to have larger masses than this. It's kind of, the neutrino sector is alleviating this part. In fact, here you can see this broad line is when the Higgs portal and all the other channels activate. Before it's kind of gauge dominated. So why we are focusing this is because also observationally CTA, Darwin, and all the newer or future indirect and direct detection experiment, they are sensitive to that range. And it's a range that is in principle less, I mean, that in the future is going to be searched. So also we're looking for models that can be potentially observable.
And in the case where you would have just, I mean, in the original Scotogenic model, it doesn't work like that, even with the doublet.
No, in the original Scotogenic model, for instance, the type 3, that is the one with triplet. Usually, if you have triplet or doublet, your mass is going to be heavier, but if you have singlet, you can go lower, but then other problems are going to arise. But in the case of the type 3, in case of your dark matter is the fermion that you do the neutral part of the triplet, you have the problem that is the coannihilation are too strong. So it's kind of, you are forced to live only in the 2.2 TeV, but in 2.2 TeV in the exact mass. Otherwise, you have too much dark matter or too few dark matter, but you cannot vary the range. With the doublet itself, you have more range to play, because it's similar to the inert Higgs dark matter model. But if you go to the construction like minimal dark matter scenario with quintuplet or quadruplet of SU2, you push everything to very heavy mass because of the larger is the SU2 construction, is the stronger is the interaction.
Okay.
Okay, so I do have one question, Roberto. So wouldn't you have also annihilation to gamma ray lines?
Yes. In fact, it was the same question that somebody did before. I mean, last week in the concept. Yes, we should have, but we didn't, because we were just testing if the model works. So we didn't have the time. I mean, we didn't want to extend a lot the same work to analyze the specific case of the gamma lines or lepton flare violation case, or because in principle, since all this connection with triplets, you're going to modify the oblique parameters. So in that sense, we try to see if at least it fits neutrino masses and some of the dark matter phenomenology that is the most straightforward. But yeah, we haven't analyzed, and we expect that maybe it could be also potentially interesting because CTA especially, they are very sensitive to gamma lines. I mean, yeah.
All right. Further questions? No, so I guess we'll just, yes, someone?
Roberto, did you consider complex values for the Yukawa couplings?
No, we only remain to real. The nice stuff, I mean, the nice stuff, I mean, we only coupled, and for us, we're real. The nice stuff for the neutrino sector itself is that, for instance, this Yukawa omega, if you put it like a vector, it's just the Yukawa omega hat multiplied by the PMNS. So in that sense, if we wanted to include CP phases in the neutrino sector, it's just there in the same mixing lepton flavor mixing matrix. But yeah, we didn't include any complex. We remain as real as possible because we really have to deal with a lot of couplings in the scalar sector. So we try to reduce at maximum but we didn't include the complex part. So I don't know what could be the implication for the phenomenology, but yeah, we didn't include it.
But so you are assuming a CP phase, a zero value for the CP phase
in the Yukawa
matrix.
Yeah. So, yeah, in the sense that for simplicity, the neutrino here is with delta, with the PMNS with delta equal to 0. Just a mixing matrix. And the Yukawas were all real. We didn't want to enter in the deep of to deal with too many phases in the model. Usually for the annihilation cross section, the CP phases are not gonna be so important. So
no, I'm wondering regarding the electric dipole moment, the contribution for electric dipole moment.
Yeah, that could be potentially interesting. Yeah, exactly. Because usually the scotogenic scenarios also are studied in that context as well.
Perfect. Thank you, Robert.
All right, so I'd like to thank all the speakers for the morning session, and now I'll pass the word to Joseph, who will lead the discussion section. Joseph?
Yes, hi everyone. So also thanks from my side for all these nice talks.